What if 1,000 imperfect guesses could add up to one nearly perfect answer? Random forest is one of the most powerful, reliable algorithms in machine learning. And to understand why, we have to start small, with a single tree. A decision tree asks a series of yes or no questions about the data, splitting it step by step until it reaches a decision. But how does the tree decide which question is best? It measures how pure the resulting groups are. This purity is measured by Gini impurity, 1, minus the sum of the squared probability of each class, or alternatively, entropy, a measure borrowed from information theory, showing how much disorder remains. But a single tree grown too deep memorizes noise instead of learning the real pattern. It becomes unstable. Change just one data point, and the entire tree can look completely different. That's a real problem. This is where a beautiful idea comes in, the wisdom of the crowd. Many imperfect opinions, combined, often beat one single expert. In machine learning, we call this ensemble learning, combining many models to get one stronger, more stable prediction. Random forest takes this literally. It builds hundreds, even thousands of individual decision trees. But here's the key. Each tree doesn't see the exact same data. Each one trains on its own random slice. This is called bootstrap sampling. For each tree, we randomly draw data points with replacement. Some appear twice, some not at all. Mathematically, each bootstrap sample ends up containing about 63.2% of 2% of the original unique data points. There's a second layer of randomness too. At every split, each tree can only choose from a random subset of features. Not all of them. Without this, every tree would tend to split on the same dominant feature, and the trees would end up too similar to each other. The strategy Random Forest uses is called bagging, short for bootstrap aggregating, train many trees, independently, in parallel. Boosting works differently. It builds trees one at a time, sequentially, each new tree focusing on fixing the previous one's mistakes. Parallel and independent versus sequential and corrective, two very different philosophies. Every model struggles with a trade-off between bias and variance. A single deep tree tends to have low bias, but very high variance. Averaging many high variance trees together cancels out their individual noise. That's exactly what bagging is built to do. For classification, the forest's final answer is simply the majority vote across all trees, the mode of their predictions. For regression, it's the average of every tree's numeric output instead. Many trees, each trained on random data, each splitting on random features, all voting together. That's the heart of Random Forest.